Okay, so finally, we can now present to you the ultimate solution for inheritance. But this should not be very new to you because you already learned about inheritance in your previous OOP course, at least for the code reuse perspective. You have seen that already. I think the main purpose for this part of the lecture will be just to show you the keyword that you actually have to use in order to do inheritance. We'll cover the more in-depth topics about polymorphism, dynamic binding next week. But for this week, at least we know how to use syntactically how to support inheritance in our code. Okay, so now conceptually you can think about you got two subclasses over here. This is not really bound diagram, just some informal sketch. Of course, if you want to draw a design diagram, you want to follow the syntax, the notation. So we got resident students, we got non-resident students. Both of them inherits from the student class. You might have a criticism right away. Well, compare with the very first design attempt, we got two classes. The second design attempt, we got one class. But now, you claim that the inheritance is more superior solution, but you got three classes. In some way, I agree with you. With just this particular example with only two kinds of students, it is true for the inheritance we need the most number of classes. However, whenever you talk about design, you really talk about scalability and also extensibility. You would want to talk about when there are many kinds of students. In that case, inheritance is going to shine. We'll see that more clearly when we talk about polymorphic collection later. Okay, I can briefly mention that also at the end of the lecture. But you're right, the number of classes is the most compared with the previous two solution. But we don't really violate any design principle anymore. So that's the plus. Okay, let's go over the code very quickly about how you can do it. So now we got a common superclass or parent class or ancestor class, right? We're going to use these terms more carefully next week. But for now, we can say parent class. Students is going to define all the common features that's going to be shared among all the descendant classes. So we got name, we got courses. You can notice that we don't have premium rates. We don't have discount rate simply because they are not really common to both kind of students. They're only unique to one kind, but not the other. We got constructor, we got register, which can be inherited verbatim to every kind of students. And also we got tuition. We are only going to include just the part about calculating the base rate. And then we can let the subclasses to redefine the inherited version of the tuition. That's something we'll see. Okay, and then let's take a look at the resident students. So now everything that's actually in the superclass students will be inherited verbatim. So we don't have to repeat anymore. That's a good thing. That's a plus for inheritance. So we got resident students over here. So we say inherits students. So the keyword you should know is about inherits. If you want to have inheritance hierarchy in your projects. And then we're going to say redefine tuition. So we're going to redefine the way the tuition is going to be calculated. More precisely, we want to still inherit verbatim how we calculate the base rate as defined in the parent class. But on top of that, we're going to say we're going to multiply that, whatever version the base rate it is, multiply that by the premium rate. That's what we're going to do. We'll see exactly how to do it. Well, how would you do it in Java though? You're going to use a super keyword, right? Well, in IFO, similar, they also got the same concept like a super keyword, just a different keyword you have to use. Okay, so constructor, and now we got a unique attributes that's only applicable to resident students, which is premium rates. And then we got set premium rates, and also we got tuition. So now we want to say for the first part of calculating the base rate, we're going to inherit verbatim from the parent class. Only the second part we're going to apply just the premium rate that's specific to this class. So the keyword we have to use is called precursor. Think about precursor is almost like a super keyword in Java. However, the syntax may be slightly different. I'm going to show it to you. Okay, for precursor. That's the second keyword you have to know for inheritance. And then after you have done the result, once you have assigned the base to be whatever the parent version of the tuition is going to return using precursor, you're going to multiply by the premium rate, and then result will be the value to implicitly return. That's just some textual description over here. Let me switch to iPad right away to tell you how you can understand about a precursor. There might be some confusion there. Students usually have. Let me clarify that quickly. Okay. So now think about we have this student class over here. So we got students over here, and then we also got resident students. We got these two classes, the parents and also the child class. the routine that we want to use the precursor is the tuition. For the tuition, you actually got these codes defined already in the parent level. And then for the tuition over here, at the child class over here, so first of all, when we say precursor, okay, precursor basically think about as if we wrote the following, as if we simply say tuition. However, the tuition here is not exactly the tuition over here. Otherwise, you got infinite recursion, right? So now the tuition over here, think about the tuition here is really the tuition in the parent class, the immediately above level. So just like in Java, you cannot say I want to call super.super. I can only call super, in which case it will only refer to the tuition at the previous level over here, which is tuition here. All right. So now the reason that I only need to write precursor is simply because the tuition over here does not have any arguments. It's simply just a query that takes no arguments. Hypothetically, let's assume, what if the tuition was defined something like this? If the tuition actually took some parameter, for example, you might took some, I don't know, maybe some Boolean, for example. In that case, how can I call the precursor in the child class level? In that case, what you should do, let me just put it here, okay? So these guys over here instead would be, okay, let me put it here, would be, you would say base is assigned to, now precursor, I need to pass some, in order to call the tuition in the parent class, I need to pass some Boolean. For example, I can say true. Okay, that's how you call the precursor. So as I said, it's as if you call the tuition from the parent level. Okay, another scenario would be, what if I want to use the precursor to call some command from the parent class, right? Let's say register, for example. Let's say for the register, I might want to say I want to simply redefine the register as well. For example, let me just show you exactly how to write it, just hypothetically, right? Let's say I want to also redefine the register. So now after tuition, I will say comma and then tuition. Oh, sorry, not tuition, register. I also want to redefine the register command, and then let me write it here. So what you would do is you're going to say register, okay, and then do, and also end. So now let's say I want to maybe execute whatever it is in the parent level, right? In that case, what I would do is by the first line, I'm going to call the precursor, which is as if by calling the register in the parent level. And because that one there will actually take some parameter, oh, let me just write a parameter, I forgot. So that'll be C and then course. So that's why precursor, I'll pass C over here, right? You can see that's how I use the precursor. But what if the command itself actually does not have, hypothetically again, what if that particular command does not have any parameter? In that case, you would just get rid of the parameter over here, right? Same. Okay, it's just that since it's a command, so it can stand alone, just precursor. You don't need to assign that to some variable. Okay, hopefully that makes sense. And then after this particular call to the precursor, you can actually can write other code that's actually additional to at the child level. Okay, so that's about the syntax of using precursor. So now let me go back to showing you just the other class, which will be very similar. Okay, so now in that case, let's go to non-resident students. Okay, that also inherits from students, and then we also want to redefine tuition because we want to apply the basic rates by applying the discount rate. Constructor make, and then discount rate, so that's unique to just the non-resident students, but not the resident students. Also, we got set discount rate, and we got tuition. So as before, we're going to say base is assigned to precursor is as if we call the tuition from the parent level, right? And also there's no parenthesis over here because the tuition takes no parameter over here. And then we're just going to apply discount rate over here, right? So you can see also for the iPad. So now it's really important for you to note that this particular precursor is as if you call the tuition over here, not the tuition here. It's not the case, right? You're calling the tuition from the parent level. Okay, let me go back to the code. Okay, so that's about the coding part, right? So that's let me just explain some terminology here. You might have known them already. So the class that's over here, that's defining common parts that's to be shared among the descendants. We call that parents, super or ancestor class. So you typically parent is just the level immediately above. Otherwise, if you say even more above, it might be grandparents or grandparents. In that case, we'll just say ancestor. I'll be more precise about the terminology that we're going to use next week. But for this week, you can simply say parent, super, or ancestor. We'll be more precise next week. And also for the child class, you can say either child class, subclass, or descendant classes. Okay, so now let's see so this part here is just about some summary of what you can use for code reuse for the inheritance solution. So basically, every time you want to use inheritance, not just in IFO, in any OOP language, it allows you to, number one, it allows you to factor out all the common features, attributes, commands, and queries in a separate class. For example, you can see all the common features among the resident students and also non-resident students, they are simply factored out into this particular part of the parent class, right? That's what I meant by factor out. So it's very common to say you might start programming several classes and you realize they do share something in common, in which case you may want to support inheritance by factoring out all the common parts for those classes and let them inherit from the common parent class. So that's a very common procedure for you to follow. Okay, let me go back here. And then, for example, the student class, right? And define the specialized version for the class, which, so you may inherit all the definition, all the attributes, commands, and queries from the student class. So for example, the name and the courses are inherited verbatim. That is why over here you can see for the name and courses, you don't see them anymore in the student class. However, they still exist. So what do I mean by that? At the runtime, how do you visualize an instance of resident students? And also, how do you visualize an instance of non-resident students? Let me do it right away. Okay, it's quite important to also realize. In the case of the resident students, so now at the runtime, when I draw later, you're going to see I'm going to draw a box. And then for resident students, RS, what attributes does it have? So you can see, according to just this particular class over here, you only see premium rates. That's it, right? Others are just routines, but it's not only just premium rates, but also the name and also courses that are inherited from the parent class. So you actually got name, you got courses, also you got premium rates. So these are the three attributes for resident student objects at the runtime. So what about non-resident students? In that case, it's very similar. You can see, according to the definition for non-resident students in the current class, you only got just discount rate. But at the runtime, you got more than these attributes that will be stored in the objects. So let me just draw that quickly. So now, again, you're going to draw a box for non-resident students. Non-resident students. And then what attributes should we have? All the attributes also inherited from the student class. So you got name, and also you got courses, and also whatever you define over here, discount rate. So that will be the visualization. Okay, you can see for between resident students and non-resident students, they share name and courses from their parent class over here. On the other hand, they got their unique premium rates, for example here, and also they got their unique also the discount rate from here. Okay, that's something for you to note. We'll talk about what the consequence this is by sharing all the common attributes from your parent class and then have some unique attribute from your own class. What the consequence is that will lead to the issue about polymorphism and dynamic binding later. Okay, so that's about the visualization here. That's also important for you to realize. Okay, and then we inherit all the attributes and then also command register. So you can see in both classes, you can see we don't declare register command anymore. You can see register is simply inherited verbatim to both classes. So you can see there's no register here, there's no register here. We don't need to do it again since we don't redefine it. Okay, and then we got tuition. Okay, tuition is only implemented partially. So it's implemented and then we redefine that. Okay, so this means code reuse and also eliminates code duplicates. So that means we will satisfy single choice principle. That's really important. Okay, and then we define new features if necessary. For example, in the case of the resident students and also non-resident student, let me show you. Okay, so here you can see for resident students, what are the new features? set premium rates and also premium rates. So these are new. They don't exist in the students. You can think about whenever you're creating a new subclass, you're basically accumulating the features. You can also add new features in that child class. And also for non-resident students, what are new? Well, discount rates and also set discount rate. These do not exist in the parent class. Okay, so that's about adding new features to the child classes. And then redefine the feature if necessary. And the syntax will be, you have to say redefine over here. Okay, you can put as many features as you like. For example, I can say I want to redefine tuition and also register. And similarly, you can say redefine over here, right? Okay, redefine is actually going to affect how, which version of the feature you're really calling at the runtime. That's to do with dynamic binding. We'll speak about it next week. Okay, so for example, tuition, you can see we redefine the tuition in both the resident students and also the non-resident students. Okay, you can see over here for tuition over here is you can think about this version 1, and then this is version number 2 by using premium rates, and this is basically version 3 by using discount rate. So now at the runtime, which version is going to be called? That's going to be important for you to decide. We'll get there later. Okay, so now we're gonna do a little bit testing, but before we do the testing, let's now talk about the 3 design criteria that we have to judge, right? Let's take a look at them very quickly. Well, the same slides. Let's talk about first of all cohesion. Do you think cohesion is being satisfied? I will argue yes. Again, if you go over just go over every class, for example, for a general students without a particular kind, they should always get name and courses for sure. And also they should be able to register and get tuition. Now for the registered students, so now you want to contrast this with the second design attempt, right? So now for resident students, we only get premium rates and set premium rates, and also tuition and also the name and courses inherited from the parent class. So it's coherent. Okay. Previously, cohesion was violated when in the case of in the case of resident students, kind is equal to 1. We still get discount rate, right? Remember in the previous second attempt, right? Let me show you quickly. In the second attempt, remember we talked about in the case where kind is simply equal to 1, you will still get discount rate. So that is not coherence. Okay, so similarly for this class as well, you can see non-resident students, we only got discount rate and set discount rate. Premium rate has nothing to do with this particular course. They are only in a separate class, so we are fine. Okay, so cohesion is no problem. It's really being satisfied. What about single choice principle? I will argue yes as well. Right, you can see design attempt number 3. Design attempt number 1 satisfies cohesion. Design attempt number 1 satisfies cohesion but not single choice principle. Design attempt number 2 satisfies single choice principle but not cohesion, right? But now design attempt number 3 will satisfy everything by using inheritance. Okay, that's really important for you to summarize yourself. So now, what about single choice principle? The answer is yes. But let's say this, I just apply something very similar. What if we want to change the registration policy? If we want to change it, is there going to be a single place we have to change? The answer is yes, because we only have to change over here about the course over here. I can say if whatever, I will do something. Otherwise, I will really extend the course, right? I only need to change over here. In that case, that's the only place I have to change. After that, this new version over here is going to be inherited actually to the 2 subclasses verbatim. So there's only one change I have to make. And similarly, for maybe the how you actually calculate the base rate, if you want to apply maybe the inflation rate, for example, as we said previously. Okay, so single choice principle is also being satisfied. If you contrast this with design attempt number 2. Over there, single choice principle was violated because you need to have explicit encoding for the kind of students. If you remember this duplication over here, for example, kind is equal to 1, kind is equal to 2, kind is equal to 1, kind is equal to 2, right? So I want to make a remark over here. this really illustrates the difference between non-OO and also OO. In a non-OO language, if you want to simulate inheritance, this is exactly what you have to do. You have to encode the kind of objects you're talking about, and then make some if statements to distinguish between the actions you have to take. On the other hand, if you talk about inheritance, in that case, you don't have to. Dynamic binding is actually going to do the trick for you. That's something I would like to maybe make a little bit more explicit, maybe when we talk about a state design pattern. Just bear with me. But if you already get the idea, good. If you want to clarify before I talk about the state design pattern, speak to me during the office hour. Okay, so what about, okay, that's about single choice principle. What about the collection of students? So that's also very important. Let me just talk about, in order to do it, I want to show you something here. So in the slides, we just got another test case over here to run through, basically create the students and also set up their courses. So now for this particular test, which does not involve any student management system, I would say the visualization would just be the same as what we did previously. Why? Remember, I talked about the visualization for the objects. If you think about it over here, I want to just do this quickly. Okay. For resident students, it's going to be name courses from here and also premium rate from here. And then for non-resident students, also name courses from here and also discount rate actually from here. It's just about a factoring. It's just about all the common part over here are factored into this particular place. So now if you compare the visualization for the first design attempt, let me mention that quickly. So everything will just work. And for the previous one, you can see the classes we define is for non-resident students, we actually got name, courses, and discount rate. And also for resident students, we also got name, courses, and premium rate. What does that mean? That means by using either the first design attempt or by using the inheritance solution, at the runtime, it's going to look similar. It's going to look identical for the objects. However, that doesn't really mean the two solutions are equivalent. Not really, because the first design attempt actually violates the single choice principle very badly. And also, for this first design attempt, as we said before, in order for you to create like a student management system, you have to create distinct linked lists, right? It's just that the visualization for the objects part over here are the same. Okay, that's the only thing I want to mention. Okay, let's go a little bit further over here about the visualization. How do we build a student management system? Okay, so this part over here has been covered, so the visualization will be just the same as what we did previously for the first design attempt. I'm gonna let you study that. Okay, static type versus dynamic type, this will be the starting point for next week. Okay, so now let me just talk about one more thing before I end the lecture. Okay, so now in order to conclude about the third design, which is to use inheritance, I want to talk about the following. How do we build a student management system? So now we actually got three classes, right? In the second design attempt, we only got one class. That's why we only need one linked list. But now, since we only got student management system since we got students, remember we got students, we got resident students, we also got non-resident students. We got three classes. So now we got two kinds of students. Does that mean we have to suffer from the same bottleneck as in the first design attempt? Like we need two arrays or two linked lists? The answer is no. Now we can simply declare linked list a collection and then of type just students. And notice that, I may have to mention a little bit about static type. Students over here is a parent class. The parent class being over here, the parent class. And then this is declared to be the static type. That means every member in the linked list has the static type students. And now dynamically, what can be those objects? In that case, it can be any of the descending classes of students, which can be resident students or non-resident students. So that's really make the linked list over here polymorphic. So this will be something I'll talk in more details next week. Polymorphic. Okay, let's get a little bit further. So now add students over here. Do we need to have two versions over here? No. you only have to say student over here. Again, the student here is the static type that refers to the parent class. So dynamically, what can you actually pass as argument over here? Any class that's a descendant class of students will actually work. In this case, it can be either resident students or non-resident students, meaning that at the runtime, what you have is this. If I have the students linked list, let's say at the runtime, I only got 2 students over here. Dynamically, the first one could be referring to a resident students, and the second one over here can be referring to a non-resident students. But that's okay, because both of them have the same common parent class called students. So hopefully you have seen something like this in the previous OOP course, but we're going to review that next week, don't worry. I just want to touch upon very quickly. And then let's take a look, register all. So now I'm going to go over every students, which is of static type students. And then I'm going to call the register on each one of them. And now, is this going to work? Yes, it is going to. This is actually a simple case, because when we call the register over here, it's just going to extend the course accordingly into the student. But we will see trickier case maybe a little bit later, because when you're, for example, when you're calling tuition over here, in that case, for example, let me just change that very quickly for you. Let's say rather than calling s.register, hypothetically, what if I call s.tuition? In this case, if I'm running through all the students over here, that means this will be the first iteration, this will be the second iteration. So now, when I say s.tuition, when I call that the first time in the first iteration, I'm going to call tuition on this resident student objects. In the second iteration, I'm going to call s.tuition on this non-resident students objects. So now, are they going to call the right version? The answer is yes, because this is the version for the tuition for resident students, and this is the version for tuition for non-resident students. So dynamically, they're going to work out. Okay, again, this is something to do with dynamic binding. And we say that for this particular students collection, every member over here may have a different dynamic type. In that case, we call them polymorphic collection. So these are all the ideas I'll talk about in complete details next week. But I think for this week, it might be nice for you to brush up quickly just about what you have learned in the previous OOP course. Okay, finally, what about the client side? If I declare RS to be of type students and RS to be of type non-resident students, in that case, how do I actually instantiate them? Let's say this. Let's say eventually I want to say this is the RS, and this is the NRS. Let's say that's what I want to create. How do I do that? Well, for the RS, I'm gonna say creates. This is so-called a static type. And dynamically, I want it to be a resident students. I'll simply put a brackets. Remember, we talked about that in lab number 0. So now I'll just say resident students over here, and then rs.make. On the other hand, for this one here, student is also the static type. So now I can say creates dynamically. I want it to be a non-resident students, and then rs.make. And then once I say add students twice, I will be able to build this particular polymorphic array. So each slot over here in the list is going to point to objects of different dynamic type. And then when I say register all, or even to maybe call different, to call the same tuition query, is going to dynamically call different versions depending on what the dynamic type is. Okay, it's a very quick walkthrough of everything that you're supposed to know from the previous OOP course. But if you kind of forgotten about it, next week will be the time to really brush up all the details. But for this week, at least go over this particular example over here to see why all the concept that you learned from the previous OOP course are really the case. Polymorphism and also polymorphic collection, dynamic type, static type, and etc. Okay, so that's about for this week. I will end here, and then next week we'll pick up from lecture 7 in the later parts.